what, I'd like to introduce our next contestant from the Faculty of Science and Engineering, Jim.
Kia ora. I'm part of this fantastic research group sitting along the front working with a new bioplastic made from dried animal blood, a cheap byproduct of the meat processing industry. You see, plastics are made of long, stringy, noodle-like molecules called polymers, and once the water's removed, what's left in blood is about 90% protein, which is a natural polymer. Why would we want to turn this into a plastic? Well, firstly, it's a renewable resource that does not compete with food supply, because it's inedible blood anyway, and secondly, the resulting plastic composts, so we can turn it into a nitrogen-rich fertiliser when we're finished with it. This way, we're saving the world by solving both fossil fuel dependence and waste going to landfill. Well, at least we're making a start. Problem is that while we can make the plastic, and we can shape the plastic into cool shapes like the plant pots you see up there, it doesn't always process quite as easily as some conventional petroleum-based plastics that we could try and replace. So in order to improve the processability, we need to understand how the material responds to both the heat and the mechanical forces that we use to shape plastics. So to get this understanding, in particular, I am researching the relaxation behaviour of this plastic. And by relaxation, I don't mean where it goes on holiday or what it watches on TV. Rather, in material science, relaxation refers to what do the molecules inside the plastic do in response to mechanical disturbances, or how do they respond when put under stress. So, to research this, I'm taking the bits of the plastic and sticking it in that machine up there, which is called a dynamic mechanical analyzer, or a DMA for short, which applies an oscillating force, or in more simple terms, it wiggles it and sees what happens. Part of the response is for the molecules to stretch, storing energy, and then bounce back to where they were when the force is removed. The other part of the response is for molecules to sort of slide past each other or flow, losing energy as heat. Now, both of those will be going on, but the ratio and magnitude of those responses depends both on the rate at which we apply the force and on the temperature we're testing at, both of which we can vary with our DMA, so we can see what happens over quite a range. At low temperatures, plastics behave kind of like those uncooked 2-minute noodles that you see over there. The chains are all sort of coiled and tangled around each other, but they can't really move much, and the result is a brittle and glassy sort of property to the material. As temperature increases, the chains start vibrating more and more until they can slide past each other in response to force, and they behave more like the cooked noodles on this side, sort of a rubbery sort of flow. However, just as if you put your pack of 2-minute noodles directly on the stove, it'd probably start burning. We have the same problem with our protein plastic. If you just start heating up your protein, it burns before there's enough thermal energy for the chains to slide past each other. So just like when you add water to your noodles, we have to add plasticizers and a few other additives to help our chains sort of relax and sort of flow past each other at lower temperatures without damaging them. Using the DMA, I can see the effect of different additives on plasticizers, on chain mobility at different temperatures, and on this transition from a glassy to a rubbery sort of melt. In time, this will allow me to predict ways to make processing easier and improve the resulting plastic. This is significant as it will expand the range of products that we can make from the blood plastic and increase opportunities to replace petrochemicals. Thank you.